So the part one was studying Ohm's law, and we're looking at analog versus digital voltmeters, and then you had some tasks to accomplish for the notebook you handed in last night, and I think that I did. Yeah, I somewhere here. I have it. I did a better job. Uh, there. Oh no, I did not. Well, in principle, you wrote it down in your notebooks. You're to verify the currents, verify the currents added up properly, verify the rules of combination, and then in series circuits, something similar. And then the part one. Okay. So let's take a look here. Now, in fact, I notice I don't have data here, so I'm going to see about opening it up another spreadsheet, so that I don't have to waste time trying to get data. Let's see, DC circuits. Alright. So this thing should have, I thought, a diagram. Ah, there it is. So yours should have this diagram with the error equation. Now don't forget that this is also the table for these error propagation equations are here. It is here. Propagation of uncertainty short form. And I'm pretty sure I've shown you this before. So we're basically interested in, let's see, 1, 2, 3, 4, 5, yeah. And then maybe the next couple. And the standard deviation is also the plus minus. And the variance is just the standard deviation squared. The big deal to remember here is that for us, any things like the sigma AB, that's the cross correlation. If the measurements if the error on one measurement affects the error on another one, but for us it's never true. So sigma AB is always 0. So you ignore anything with sigma AB. I use this table. I write a paper and I need to show results. I go back and double check these equations. You'll see there's the long form here. There's amazingly heavy duty math behind this. Blows my mind. Yeah, where is it? Error propagation. Yeah, that's the whole Wikipedia article. It'll make your head spin. Makes my head spin. Okay, so what happened? There it is. And then, okay, so I would caution you. Well, no, these are similar values, but I'm not going to do the whole thing like I would do for the 1200 people. So this is about the analysis here. So we measure, for example, in this case, I measured 105 or 10.5 milliamps. So when I type that in, 10.5 E minus 3, I may have gone through this already. And then if I see something, the way that you do the plus minus on a digital meter, so I must have done this, right? I'm bringing up annotation here. So if I see 10.5 milliamps, then I look for the last digit on the right, and that's in the tenths. Whoops. So then the plus minus is 1/10 divided by 2, which is 0.05. So here then, somehow I don't know if I believe that, but let's find out. Oops, I gotta make this a mouse again. Here we go. 0.05 E minus 3, excuse me. Yeah, I thought so. That was off. And then I measured 5 volts, so this one here is 1/2 of the hundredths place, so I have a 5 in the thousandths place. And this one, that looks off as well. 10 milliamps, 10 to the E, because I have to convert it to amps, so that's why I do the exponent. So that read 10.0, so this is the same as before, 0.05 E minus 3. There we go. And then I have R equals V over I. Oh, this is just a number. Okay, so that equals the voltage, divided by the current. I'm pretty sure I went over this last time. Same thing here, equals the voltage divided by the current. Okay, so it's asking us for the fractional error. And the definition of fractional error is the plus minus divided by the value. Right there. So that's equal to the plus minus divided by the value. And in this case now we can just use the fill handle. Whoops, too far, because we can't do that yet. And again, this is equal to the plus minus divided by the value. Okay. So now what we need is we need to figure out what's the plus minus on our R. Now, I thought of this really great analogy to, it's funny, yeah. I have a wheel on my pad that's, oh, there's a lag too. Uh-oh. Wait a minute. Oh man. Okay. So whenever we multiply or divide, well, any two numbers, add, subtract, multiply, divide. So we have, oops, I need this to be, okay, drawing, I want to draw. So we have R equals V over I. And there's a plus minus V and a plus minus I. So what is plus minus R? Well, one way we could do it is we could put on the top V plus minus V over I minus plus minus I. And we could call this some like an R max. So we could say that plus minus R would be R max minus, is it minus? Yeah, minus R min divided by 2, and then we'd say that's our plus minus R. But the thing is that we don't expect that when we measure current and voltage that every time we measure it, we kind of expect that we're doing middle of the road values. You know, even though it's a plus minus something, we figure most of the time we're getting it right. So it really, and if you do this out, you'll see that plus minus can get quite large. So the analogy for this, which I really like, because and I just thought of it recently. So we know about right triangles, right? And we know that c squared equals a squared plus b squared. And the key here is right triangles. And we also are assuming, remember we said sigma AB is equal to 0. And that means that the two measurements have no correlation to each other. So most kids, most students, and most people think that the definition of orthogonal means 90 degrees. But it only means that in Euclidean space, x, y, z space. The definition of orthogonal, it means that if I make a change on one axis, the x-axis, there's no change on the y-axis. And again, in Euclidean space, that means 90 degrees. So the analogy is that if I make a measurement in the current, with current, and there's an error along the current axis, it has nothing to do with what's on the voltage axis. But of course, it has an effect on the hypotenuse. And so, at the end of the day, if we call this the fractional error on, say, the current, and this is the fractional error on the voltage, then if we add them with the Pythagorean theorem, we can get the fractional error on squared of the resistance. And that, if you study the table, that's exactly what it is. And then if I take the square root, just like if it was the Pythagorean theorem, I get the fractional error on R. And you see that, of course, now this is going to be a smaller number than if I did it the other way, but it kind of gives us this feeling that if we have two, I think of it as I've got these two vibrating nodes, and then I'm multiplying them once in a while. And most of the time, they're going to be in that small middle area. And when you add in quadrature, that's called adding in quadrature, and that's what you get. So let's go. So that means that the fractional error on R is equal to the square root, open parentheses, of the fractional error on I squared, plus the fractional error on V squared, and Y. What did I do? Oh, I forgot to put the 2. And so now I've got a fractional error there. I could always make it into scientific notation. And once again, this equals the square root of this fractional error squared plus this fractional error squared. And why does it, I guess it just happens to be that way, huh? Okay, well, that makes sense. I believe it. And then, of course, because of the definition of fractional error, if I have the fractional error on R, I can get the plus minus by multiplying the fractional value of error of R times R, right? Because the fractional value is defined as plus minus R over R. So this implies that if I multiply the fractional value of R times R, I end up with the plus minus R. So this equals the value I got. Yes, Jacqueline, but I'm according to my machine directly. Thank you for asking. Yeah. Times the fractional value. So there's our plus minus. Notice that, let's get the plus minus here, equals R times the fractional value. And I want to make that a number. Notice that the difference between them is 24 ohms, and the plus minuses do not cover the difference. So you're to do the rest of your analysis. So for example, now this is the analog value is 476, and the plus minus is 2.32. The digital is 500. The plus minus is 2.55. The nominal is 500. The tolerance is 0, really. I mean, there's no. That's the one drawback of Tinkercad, because it turns out in the real world, it's the nominal value is what's written on the resistor, but they don't end up being the same. They don't. So one of the things here would be to not only compare analog and digital, but if it says 10% tolerance, did we get our money's worth? But we can't do that. So your job is to fill this thing out and notice any differences and explain why there are differences. And it's basically about analog and digital. And I will tell you that it's basically that it has to do with the input impedances of the two voltmeters. And remember the circuit. Yeah, here it is. It's all here. You have the device under test, current through, voltage across, and input impedance. And I even hinted at it last week to some degree. So it's up to you guys to figure out why. Well, first of all, I don't make sure there is a difference. Fill that rest of that table out. Okay, so I'm going to stop this one and then I'll start a new recording.